Welcome back to Applied Physics Lecture Series, Unit 3 Optoelectronics, Lecture number 4. LED, its structure, composition, and characteristics. So, what is this LED? So, the abbreviation of LED is nothing but light emitting diode. So, the principle behind the operation of this LED is nothing but simply light emitting diode is essentially a PN junction diode that gives off light when it is operated under forward bias condition. So the amount of light which is emitted is directly proportional to the forward current. How much amount of light, how much intensity of light that we are going to get, that will depends upon how much amount of forward current that we are going to apply in the circuit. The wavelength of the light emitted and hence its color depends upon the band energy, which is nothing but forbidden energy gap of material which is forming the PN junction. So because the forbidden energy gap expression is h nu, which is nothing but hc by lambda. So from that we will get the wavelength is hc by eg. Here eg is the energy gap and h is the Planck's constant, c is the velocity of light. Here h and c are constants. Therefore the value of lambda depends upon wavelength, depends upon the existence of energy gap, how much amount of energy gap present. Based on that value we can able to get the color. And if you observe the symbol for LED, it is a normal PN junction diode symbol, but we are having two lines which are indicating light, that is the symbol for LED. And if you observe the structure of this LED, this is the structure and you can able to see in this one. So in a surface emitting LED, light is emitted which is perpendicular to the PN junction plane. An N-type layer is grown on a substrate and a P-type layer is also grown on it by the process of diffusion. If you observe this one in the diagram, at the bottom we are having a gold film cathode constant which acts as a substrate. On that one we are having epiaxial N-type semiconducting material. On that one we are having a P-type substrate which is diffused, and at the top of that P-type we are having two metallic film connections on both sides. So exactly at the middle we are having a small window, usually which is made up of with glass. So from that light emission takes place. The P layer is very thin to prevent the loss of photons due to the absorption in the layer. So metal contact is present on the P layer, so such that some part of P layer allow the photon to escape. Metal contact is present at the bottom of the reflecting the photons into the material and to provide the electrical contact. So at the bottom we are having a metal contact, so which is used as an electrical contact. So with help of that one we can able to reflect the photons inside that medium. So as a result we can able to improve the efficiency of the light. The generated light may suffer total internal reflection, so that will takes place at the bottom of the semiconductor air interface, and hence the device is enclosed in an epoxy resin of a suitable refractive index so that the photons will be escaping out. So how it will work? So already I mentioned, so this is a normal PN junction diode which will be operated in the forward bias. Electrons from N side get injected into the P side, and whole injection takes place from P side to N side, which is very less because here the P type substrate is very thin. Electrons injected into the P side recombine with the holes, which results in a spontaneous emission of photons. This is very important. So here spontaneous emission takes place in the process of LED, and stimulated emission process will take place in the operation of laser. This effect is called as injection electroluminescence. We are injecting the charge carriers, we are injecting the light. As a result, we will be getting the better light in the form of electroluminescence. These photons should be allowed to escape from the device without being reabsorbed. The recombination can be classified into the two categories. One is direct recombination and other one is indirect recombination. So what is this direct and indirect recombination mechanisms? So in case of any LED, so we are having a valency band and conduction band. Usually valency band is occupied with holes and conduction band is occupied with electrons. Meanwhile, in between those two, we are having an energy gap. So in a direct band gap semiconductors, the topmost energy level in the valency band and the bottommost energy level in the conduction band are aligned exactly in the same way in the direct manner. So as a result, recombination takes place very easily. That means the electron which is coming from the conduction band directly recombine with hole which is present in the valency band. As a result, X amount of energy will be coming out in the form of light or in the form of photons. And in case of indirect band gap semiconductors, the topmost energy level of a valency band and the bottommost energy level of a conduction band are misaligned. So to cope up these two, so first of all, momentum will be regained, and we have to match up this momentum. Then only recombination will be takes place. That's why efficiency is somewhat decreased, but the efficiency in case of direct band semiconductors is very, very high. What are the basic differences between these two types of band gap semiconductors? In a direct band gap semiconductor, the minimum energy of the conduction band occurs at the same value of the momentum vector as the maximum energy of the valence band. That means there is a relevance between these two. But in case of indirect band gap semiconductor, the minimum energy of the conduction band and maximum energy of the valence band occur at different values of the momentum vector. So the efficiency of the transition is very good in case of direct band gap semiconductor, but in case of indirect band gap semiconductor, due to mismatch of this momentum component, the probability of the direct electron hole recombination is very, very less. That's why when compared to the direct band gap semiconductor, the efficiency is somewhat reduced here. And gallium arsenide is an example for direct band gap semiconducting material. Gallium phosphide is the example for indirect band gap semiconducting materials. And if you observe the characteristics of LED, you have to draw the graph between current and voltage. So here the graph is exactly in between forward current, which is taken on the y-axis, and the current value is measured in milliamperes. And on the x-axis, we are taking the forward voltage. So one of the major characteristics of LEDs is its color, because we are having so many colored LEDs. So already I mentioned the color of the LED depends upon the energy gap which exists in between the valence band and conduction band. For example, if you take gallium arsenide semiconductor, it emits light in the infrared region. In the same way, gallium arsenide phosphide so emits a red or yellow color. So if we take gallium phosphide, it emits red or green color. So we can able to see different colored lasers. So almost all the different colored LEDs, I'm sorry. So almost all the colored LEDs you can able to see. And where we are going to use these LEDs. So in our day life, we are having so many number of applications with LEDs. Out of those, the very, very important and daily applications are, those are used as indicators and light source in the fiber optical communication system. A number of LEDs may be grouped together to form a display. And other important routine application is LEDs will be used as traffic signals. Thanks for watching.